and he just did math on the side. Dr. Clark was the big mathematician, so he just sort of shrugged it off, said, no, you don't know what you're talking about. I'm the expert around here. And they started going back and forth with their letters, and some of their friends got involved, and all that, and got a little heated. And finally, this other mathematician comes along and said, well, okay, Descartes' not going to listen to me. I'm going to show it. I'm going to do it myself the correct way. So he goes through it all, and he does it. By the way, calculus had already been invented at this point. And you could actually come up with this equation using calculus easier than the way either Descartes or this other guy did it. But he does it, and he does it correctly, and he comes up with the same equation. Now, his name was Pierre Fermat, F-E-R-M-A-T. If you did the math, you may have heard the term Fermat's last theorem. Anyone heard that in math? You see the Pythagorean theorem. A squared plus b squared equals c squared. Is it possible to find integers a, b, and c that fit that equation? Sure. How about 3, 4, 5? 3 squared plus 4 squared is equal to 5 squared. The Pythagorean triples. And some mathematician somewhere has shown that there's an infinite number of those integers, triple integers, that will fit that equation. Okay. Well, Fermat was looking at all this. He was a lot into what we now call number theory. For the most part, at that time, it was very theoretical math. Nobody knew if it had any particular use in real life. Nowadays, there's a lot of number theory uses, in computers and all sorts of stuff. But what he came up with was that, what if you've got a to the n plus b to the n equal c to the n power, where n is an integer. So, yeah. A to the first plus b to the first equals c to the first. 1 plus 2 is equal to 3. A squared plus b squared equals c squared. 3 squared plus 4 squared is equal to 5 squared. Okay, that works. What he said was that if n is an integer bigger than 2, that there are no integer values for a, b, and c that make that equation work. At least one of them is going to be some, unending decimal sort of a thing, irrational number. And after he passed away, some of his people, looking through all of his books and papers and everything, in the margin of this book, found this equation. And in there, Fermat had written, I've found a beautiful proof that this is true, that for any integer bigger than 3 for n, that there is no integer for a, b, and c that makes it work. But I don't have time, I don't have space to write the proof here. And that's all they found. So after that, by that time, Fermat was known as a pretty good mathematician. So other mathematicians started looking at that, trying to come up with what was his proof for that. Nobody could come up with the proof. And by 1900, somebody had come up with, here's the 5 most famous unsolved problems in math, or something like that, and offered some big monetary reward if anybody could come up with that. And people tried to solve it, and they tried it, and no one could come up with a proof for that theorem. Until about 2000, somewhere around 2002, between 2000 and 2005 maybe, somewhere in that thing, a Princeton mathematician, besides just doing his classes, he basically worked on this for about, 8 or 10 years, something like that. Didn't do hardly anything else. Wasn't Mary. He'd do his classes, he'd work on this the rest of his time. And in some a math conference over in London, he presented some papers that essentially said, I've got this proof. Fermat's theorem. So other people started checking it out. We got to make sure everybody agrees that yes, you do have the proof. They found a couple of small errors there, and so he went back and spent another year working on those, and then presented his final papers. And so everybody said, okay, whatever his name was, has proven Fermat's last theorem. Big proof in mathematics. Unfortunately for Fermat's reputation, I guess, although it's not really, but the mathematics that this guy was using to prove that you can't find A, B, and C integers if n is bigger than 3 or bigger than 2, he was using mathematics that hadn't been even invented at the time of Fermat. And so people say, well, okay, Fermat came up with this idea, but no, he probably really didn't have a proof himself that that would be a true statement. Anyway, that was Fermat, and he came up and he did the mathematics correctly, and came up with Snell's law. And what he used, Snell had, yes, mathematically come up with that, even though he'd made a couple of math mistakes that Fermat caught. But his ideas were wrong as to why it was doing that. Fermat comes up with the reason for why light bends as it goes from one medium to another medium. And that is that the speed is changing. The speed of the light changes as it goes, like from air into water or glass or whatever. And this index is related to the speed of the light in whatever the medium is. And so we've got the index is the speed of light in a vacuum. So that's the 310 to the 8th or 2.99, whatever, 10 to the 8th, divided by the speed of light in this medium. Now, speed of light in a vacuum is the fastest light can go. Can't go any faster than that. And so the speed in some other medium is going to be less than the speed of light in a vacuum, which means that n is greater than or equal to 1. It's 1 if it's a vacuum, because then the V is equal to C, just FC over C, which is 1. But if V, or if n, the index, if the medium is something other than a vacuum, then the V is less than C, and therefore the n is bigger than 1. Now, for air, that's not a vacuum, but we're going to use n equal 1 for air, because it's almost the same index. Again, it's about the third or fourth decimal place before it gets away from 1. It's bigger than 1. We'll use n equal 1 for air, but technically n equal 1 is if it's a vacuum. And then, again, if you've got other mediums, we'll change that. Either give it to you, or maybe you're solving for the index by using some of our equations with refraction. So that's refraction. As light goes from a smaller medium to a bigger medium, so if the n gets bigger, the sine of the angle has to get smaller, and if the sine is getting smaller, the angle is getting smaller. So it's bending toward the normal if you're going from a smaller index to a bigger index. But if you're going from the bigger index to the smaller index, if the light was coming this way, it bends away from the normal, gets to a bigger angle at that point. So the bigger the index, the smaller the angle, and vice versa, the smaller the index, the bigger the angle. And the bigger the index, that means the smaller the speed for the light wave is. So it's changing direction. Books will show you examples of like mechanically as a mechanical analog of this, if you're driving your car down the road, and this could have happened this last couple of days here. Say your right side of your tires get off into the mud, get off the pavement and gets onto the mud. What tends to happen to the car when that happens? Especially if you're not holding real tight to the wheel or to the steering wheel. It tends to veer off of the road, right? Because it's like the tire can't rotate the same speed when it's in the mud as it can when it's on the pavement. Or you've got some less friction there. And so that wheel might start spinning, the one that's on the pavement is still trying to roll, and it would tend to veer off of the roadway. And you'll have people having wrecks because they'll start to veer off and they will overcorrect and come back and then maybe hit somebody coming from the other direction as they overcorrect coming back. But that will tend to happen. So that's the same thing that's happening with the light. As it gets into this higher index medium, it slows down, and therefore the wave, the different parts of the wave, can't keep up with each other. If you did this with waves as opposed to these rays, so here's this wave coming in. This part hits it, but now this part of the wave, it's now gone into this new medium, it's slowing down, and so it's maybe curved like that, and then you got it this way, and I can't draw these things the way I'm supposed to. And so these wave fronts coming out in here, so you got the light coming this way, but now they're going that way. They've bent and changed directions because the wave itself is slowed down. You get into the quantum mechanics of it and everything. You have to see what's happening as these light waves interact with the particles that make up the medium at that point. But that's the idea. So we've got Snell's law. How do these angles and these indexes relate to each other? As an example, let's say we've got a prism. It's a 60-degree prism. So you've got a piece of glass, equilateral triangle shape, and we're going to have light coming into it. And this is parallel to this bottom surface down here. So if this is 60, that's 60. The angle to the normal then would be 30 degrees. Okay. Well, if I've got air out here and glass in here, so this end is going to be 1, this end is going to be 1.5. What's going to be the angle of the light inside this glass prism? Well, I'm going to a bigger index, so I ought to go to a smaller angle here. What would that angle be? And so I've got now 1 times the sine of 30, that's on the air side, and that has to equal 1.5 times the sine of the angle on the glass side. So we've got sine of 30, divide that by 1.5. And that gives me 0.3 forever is equal to the sine of the angle on the glass side. And so I'll do an arc sine of that angle, or that number, and that gives me 19.47 degrees on the side that is the glass. That would be this angle. Now, with a prism, though, the light, it didn't just go into the glass, it comes back out the other side. So as it comes out this other side, what angle is it going to be at as it comes back out into the air? Well, at that point, I need to know what is the angle inside the glass as it hits this side glass to air in the face. Just to work you through the geometry of all this, or the way I approach it anyway. If I look at this vertex to here, to the normal, this normal, and there, that's a four-sided figure. In any four-sided figure, the total angle inside the four-sided figure is 360 degrees. Because you got two triangles, you cut across the diagonal there. So this angle plus this angle plus this angle plus this angle is all equal to 360. But these two angles are 90 degrees. They're to the normal to that surface. And so 360 minus these two 90s says this angle plus this angle ought to equal 180. So I've got this angle up here and this angle here are going to be 180. Well, but if this is equilateral, this angle is a 60. And so what is this angle? Well, that would be 180 minus the 60, which is then 120 degrees. So this angle is 120. Well, this angle is 120. This theta 2 is my 19.47. And this ray and then the two normals form a triangle. And so I've got the 180 of a triangle minus the 120 minus the 19.47 is going to be the angle going from the glass out into the air. And so that angle again is, so I've got actually just 60 minus that angle. And so another way you can approach it with a prism sort of a thing, you know, this vertex angle, then this angle is going to be the vertex angle minus this angle. If theta 2 as it goes from air to glass. And then from the angle from glass back out to air, that angle is the vertex angle minus the first angle there. Okay, so I've got the 60 minus that, which is now 40.53 degrees. And so I can go back to Snell's law and say that it goes from the glass here, so 1.5 times the sine of the 40.53 is going to equal 1 times the sine of the angle back on the air side as it goes back out into the air. Now, drawing wise, I'm going from the bigger index to the smaller index. It goes back out into air. And so if it goes from a bigger index to a smaller index, then the angle ought to become a bigger angle. So if this is 40.5 in here, angle coming out this way, which is now my theta on the air side, is bigger than the angle on the glass side. And so mathematically I should end up with that. So 1.5 times the sine of 40.5, 3 dot dot dot, and do the inverse sine of that. So that gives me an angle of 77.1 degrees on that side. And again, yeah, I've rounded them here, but on the calculator they're unrounded until I get to this final one here. So yeah, bends to a bigger angle. Now, if it wasn't a prism, now, don't look through prisms just a whole lot. But we look through windows a lot. And a window tends to be, the two sides tend to be parallel to each other. Here, this side and this side are not parallel. So what if they're parallel? So here's our window. We've got light coming in here. And so we got n equals 1 on this side. We got n equals 1.5 for the glass in the window. And then we're going back out to air on this side, so n equals 1. If I make this my, let's make it something different. Let's make it 20 degrees. then the angle on the on the glass side, I need to draw that bigger. Let me see easier. Here's the normal angle on this side. Here's 1.5. So I've got the 1 times sine of 20 is equal to 1.5 sine of my theta 2. So I've got sine of 20 divided by 1.5, and then take the inverse sine, and that gives me now 13.18 degrees. That's this theta 2. And then as it comes out on this side, well, if these two are parallel, these two sides, then this angle and this angle are the same angle. So that theta 3, and so theta 2 is going to equal theta 3. And so now I've got the 1.5 times the sine of the 13.18 is equal to 1 times the sine of all this one over here, theta 4. So back out into the air. And so 1.5 times sine of that answer, and divide by 1, and we take the arc sine, and you get exactly 20 degrees coming out on the other side. So this one coming in, and this one coming out this side, they are parallel to each other. But it's been shifted. This, if this wasn't going through the glass, it would be going this way. And so it's been shifted over some because it went through the glass and bent as it went through the glass. Now, two sides of the glass parallel, yeah, it comes out parallel to itself, but it has been shifted over. And it's been shifted by some distance there. I think it's the 5th or 6th problem says there's a problem that asks you how big that distance is. So it gives you like this thickness. And so if you know how thick this is at that point, and then you can figure out basically where it hits over here. Some triangles at that point, you can figure out the distance that's shifted sideways here, which would be the same, not as the distance here to here, but between those two parallel lines, that distance. So, when I think about it, I'm looking out the window and I see like there's a light pole on the old track stadium that's back there, and it's vertical, but it's at an angle to the window. So technically, when I see that, what I'm seeing or what my brain thinks of, it's not really exactly right there. It's over a little bit from where I'm seeing it. I think it's a little bit to the left. It's actually a little bit to the right of where my brain says it is at that point. Now that window's not so thick, it's going to be very much different. You have to have a pretty thick piece of glass there before it's going to shift significantly. But it has shifted. And so you're not seeing it exactly where it is. The only time you would do that is if you were looking at it and this angle on this side is 0 degrees. Because if it's coming in perpendicular to the surface, it doesn't shift directions. Because you've got sine of 0, which is 0. And so the other angle is 0. So it just goes straight through without shifting if it goes in perpendicular to that surface that it's from one medium to the other medium. But if it's at an angle, yeah, there is a shift that's occurring there. So that would be, if you got like a parallel lines. Here, they're definitely shifted. It's coming out this direction. And so it was going in this direction, and so this way, well, now it's coming out that way. It's been shifted over some at that point. The thing that happens with prisms, though, and Newton did see this, so he realized the light was bending, was that different wavelengths are going to shift different amounts. Different wavelengths have different indexes of refraction. So if we looked at the index versus the wavelength, so the 700 is around the red and the 400 is around the violet end of the spectrum. Like 400 here, nanometers, and 700 over here. For most transparent materials, 400, the violet end is going to have a higher index, and the longer wavelengths are going to have a shorter index. That may be very highly exaggerated for most materials, but it would tend to be that way. Water does that. Glass does do that. The violet has a higher index than the red end of the spectrum, and everything else somewhere in between those. So if we had this, and instead of 1.5 for just, that's just sort of like an average, what if this violet was, say, at 1.53, and the red 700 nanometer was at, say, 1.49? What's going to happen to the different colors then as they go through this prism? If they went through the, you'd have a little bit of that effect that went through just a parallel pane of glass, but it wouldn't be as big as you have going through the prism. Well, if you have that, then I don't have, it's coming in at the 30 degrees. I don't have the same angle anymore. So for the violet, the 1.53, that theta 2 as it goes from air to glass. So the sine of 30 divided by the 1.53 and do the arc sine, and that gives us now 19.07 degrees. And so call this theta 3 on this side, the theta 3 then is the 60 minus the theta 2. So that minus the 19.07 gives us now 40.9 and rounded off 3. And so as it goes back out into the air, I've got the 1.53 sine of the 40.93 equals 1 times the sine of theta on the air side, or call this violet, theta sub d for violet. And so the violet coming out back on the air side, 3 times sine of the 40.93, and do the arc sine of that, and I get something that's not good. Oh, shoot. We don't want to get into that right now. We're going to have to change numbers. Sorry. Let's make this, see if the 1.52 will work. Sine of 30 divided by 1.52. Sine is that, and 60 minus that, and then 1.52 times the sine of that answer does work. Okay, so if it's 1.52, then we have 19.20 And this becomes the 40.795. Two, and this is going to be arc sin. That answer becomes now 83.3 degrees. And so the violet coming out here at 83.3 degrees. Well, what about the red in the spectrum, the 700? So I've got 1 times the sine of 30. They're both coming in at the same angle in the air. It's white light coming into this prism is equal to the 1.49 times the sine of theta 2. And so my theta 2 for the red end. So sine of 30 divided by 1.49 and the arc sine, and that gives us 19.61 degrees. And so the theta 3 for the red is going to be the 60 minus the 19.61, which is now 40.39 degrees. And so I've got the 1.49 sine of the 40.39 is equal to 1 times the sine of theta for the red end as it comes back out into the air. That answer and do the arc sine, and that now gives us 74.9 degrees. And so the red, it's a slightly larger angle as it goes from air into glass. Here's violet, here's red. And then when it comes back out, now it's only at the 74.9. To the normal, the violet was at the 83.3. And so here's the red on this side, here's the violet there. If you put like a screen over here, what you end up with is a rainbow of colors going through violet through red as it goes out there. And so you've split the white light into all of these different colors, which is what Newton was able to do. He was able to see that happen. Of course, if you arrange another prism on the other side, then you can actually take all that, those different colors and cause them to go back together, and you end up back with white light, which again we did. So different colors, different wavelengths have different indexes, and different indexes then give us different angles